welcome back to the next lecture of the topic, and this is again continuing about the topic of convolutions of the thing that we want to model the random walk. So for this purpose I will talk about this notion of iterated convolutions, iterated convolutions. And here, as I mentioned, so if you have the convolution, you have a convolution of two probability measures, you could continue this forever. Like you could take large n-fold convolutions. If this is happening n times, we just use this kind of notation mu star n as the notation for this n-fold convolution. So it's kind of like an iterated convolution for any natural number n. And this is kind of with the convention you could have in the proofs. This is useful to write that if you take zeroth convolution, then this is just Dirac at zero. You don't basically do anything. So then this works in this way. And so if you now do this kind of like definition of the convolution, you can then, if you remember, recall the transfer operator, I think we use this notation T mu, and if we applied it for a function, we had this idea that it's just a mu convolution with f. That's how we defined it. So f, which is a function from zb to c. So then, if you iterate this, if you take this to some power n and apply to this same function, that this is just basically the iterated convolution, and you're taking this, so if you take it once, it's just one. So this is just iterated convolution n convolution with the initial condition in n. So when you're transferring the initial state that you started for the whole process, then this is basically connects back to the definition of transfer operators that we have considered. And what the kind of like use of this is that now we can model random walks using this operation, this iterated convolution, to make this like precise. So let's talk about random walks. So random walks. So let's first fix probability distribution mu p from 0, 1, which is a probability distribution, and define random variables on zp as follows. So we say that t1 and t2 up to, let's say, tn are random variables in zp with distribution mu if probability that this, let's say one of these one tj, has the value t is equal to mu t, this point probability, and this is for every t in zp. For each j from 1 to up to n. So you basically have like a sequence of possible random choices, and each of them are chosen with this probability, with this mu. And what happens basically if you draw the picture over here, and you say you have your group, let's say this is like a group of 8 elements this time, then we have your probability measure. I don't know, mu could be like somewhere here, like maybe it doesn't have some mass on some points, and then there's more mass in some other ones, and then here like this. Then what happens here is basically that every time you make a random choice, that it's one of these numbers. Maybe the first time you landed into this one, and then the second time you landed into that one, and then the next time you landed into the other one, and so on. And so that's kind of the choice of the random process, that there's maybe more likely to reach some of the points and the less one. And now a random walk could be defined as follows. So, sorry, this is the wrong color. So the definition, random walk on ZP is then the random the random sum T1 plus T2 plus Tn. So this is, each of them are random variables. So these are all random variables with the distribution R mu. So what would be then the distribution of this random variable? Well, if each of them, like mu, if you look at this property, so if each of the mu's have if the tj's have distribution mu, so the probability of hitting one of the points t is a mu, then if you take a sum of these, that means you're basically taking n times the possible random choices of choosing mu. So hence the distribution of this random walk T1 plus T2 plus and so on until Tn is actually mu star, it is this iterated convolution n times, as the probability, well, it's just, you like see this, that if this probability Tn is equal to, let's say, some value t, then this is equal to mu star n at the point t, when you compute the probability of this. But here, I'm assuming these are like independent choices. So you could say that these are these choices here that you choose, these are independent choices of each other. So in the probability theory, it's typically important whether you like choose your variables in the random walk independently of each other or independently of each other. So here we are like choosing these independently. So in that situation, we have that the distribution of this random sum will be given by the iterated convolution that we have here. And this is very important because now, in order to analyze any properties of random walks, we only need to compute this, basically these numbers. And it may look a bit like weird that, okay, why are we like going into this complexity to define these kind of things? Why do we need to use the convolutions and everything? It's just because of the fact that if you want to translate the ideas from the group theory into this notion of random walks, then having this kind of like more analytic structure, or the way of defining it using these convolutions, makes it easier to compute these probabilities actually. And this is something that what I'd like to maybe little bit give you heuristics about. So maybe if you like compute, for example, the probability of events. So let's say a simple example, maybe a very simple example would be that, so let's consider xn to be this random walk T1 plus Tn be the random walk on ZP, let's call it driven by mu, i.e. this, just when I talk about it's driven by this mu, it just means that each of these probabilities of tj's equal t is mu t. So the distribution of these is equal to the distribution set. And we could then ask something like this, that let's say if S and T are values in ZP, then what we could ask the probability of this event. That let's say we initially start from the value s, x1 is equal to s, so we the first value we obtained x1, which is t1, we obtained this equal to x, and then after n steps we move to the value t. So somehow in the group, if you study the group of the random walk and you start from the point, let's say s, and then what is the probability of the random walk after n steps reaching the state t? So that could be like a possible state. It could go back and then all the way back and then so on. And what's the probability of in the group ZP reaching from S to the state P? Well, then this can be then defined in this way that you could talk about this because these are independent choices of like each of each other. You could then define this to be just the probability of x1 being equal to S, and then because xn choice we don't we think about these are chosen independently of each other, and then you have this xn is equal to t. So here this is very careful, like with the convention what we talk about, that if does it depend on the xn choice on the t that you have already chosen. But here you think about these as two independent processes. X1 is a different process from xn. You're choosing a different value at each point. So it's an IID process in this sense. The nth choice doesn't depend on the first one. And then this then is that you can compute this. This is the mu s, that's the definition. And then this is now, you just define this to be star n of t. That's the probability of this. I had this in the definition 3.19 in the lecture notes, if you want to compute that. So that's, for example, an example how would you compute the probability of this event. And you need to compute these convolutions, for example, if you want to get into this probability. And this is how, for example, later on when we have these like questions about like shuffling decks and random walks and like shuffling Rubik's cube and other these questions, you can formulate those as a probabilistic event like this, that it's like, for example, how many shuffles does it take to mix a deck or something like this. But then you can actually, that event can be rewritten as a some convolution of something like a convolution of some measure, for example. And then you can maybe analyze that instead. And later on we will see that analyzing the iterated convolution is very easy using harmonic analytic tools, and that's why we are like really setting this up to this kind of situation all the time. Okay, so there are other examples in the lecture notes about this topic, but this maybe gives you a little bit of an idea what the random walks and how they connect to the convolution here. Okay, so thanks a lot.